Algebraic geometry is the study of zeros of polynomials. So we start this by a quote of Sophie Germain. Algebra is written geometry. Geometry is drawn algebra. So let us see this quote in action. So consider the circle. This is drawn in R2, but you think of it as C2. And corresponding to it, you have its equation, which is x square plus y square minus 1 equals to 0. Now you can write this in terms of algebra. So corresponding to C2, you have cxy, and this equation is 0 in C2. So you modulo out the ideal from this ring. So this is called coordinate ring of this equation. Now another example. So say you have a curve like this, and this curve has an equation y square minus x times x square minus 1 equals to 0. So this is again in C2. Corresponding to this, you again have a coordinate ring. This is cx comma y, which corresponds to C2, and you modulo out this ideal. So this ideal is 0 in C2. It also becomes 0 in this ring. Now again, this is called coordinate ring associated with this polynomial. Another example. So say you have y square minus x square times x plus 1, again in C2. So this is 0. This corresponds to this curve. Now you can write here cxy corresponding to C2, and then modulo out this ideal. So you have geometry and you have algebra. So let us now start the course. So you set K as algebraically closed field. So you can think of this K as, say, complex numbers, and you fix a ring A, which is K x1 x2 all the way to xn. So for example, you can talk about cx comma y. Now you can plug in values from kn into some, say, f in A, and then you can get back k. So this is nothing but evaluation map. For example, f is just this function, and you're working in ring cx comma y. So you plug in 2 comma 1 in here, then you just get 4, which is an element of c. So you are evaluating this polynomial f at point 2 comma 1, and that is precisely what we are doing here. Now instead of kn, in algebraic geometry, people write it as a subscript k and superscript n. Now this just shows that origin does not hold any special place here. So now consider a subset S of A, that is a bunch of polynomials in this ring. Then we can talk about its zeros. So x is part of Kn such that f of x is 0 for all f in this set S. Now these are common zeros. So all these polynomials vanish on this set. So for example, if you have a single polynomial here, so this set consists of a single polynomial. So they say that single polynomial is y square minus x square times x plus 1. Then this figure which is drawn here, this entire curve is the set of zeros. Now notice that we are talking about common zeros. So if you put all three polynomials in here, then you do not have all three figures. You have only a small subset of points on which all three of them will vanish. Now the set S could contain infinitely many such polynomials. For example, you can consider the ideal which is generated by infinitely many polynomials. So this ideal could be the set. So in fact, we are going to consider ideals rather than sets. So for these infinitely many polynomials in the set S, so there could be infinitely many polynomials in the set S, you could consider an ideal which is generated by these infinitely many polynomials. So instead of set S, you put an ideal here, and then you can have vanishing set of I. So the zeros of S or vanishing set of S, now you have vanishing set of I, because instead of a set you're putting in an ideal. So you can write above as V of I. Now since K is a field, we know A is a Noetherian ring. Now since A is a Noetherian ring, any ideal of it is finitely generated, and so this ideal I, which is generated by infinitely many polynomials, this is actually generated by a finite set. So it's generated by a finitely many polynomials g1, g2 all the way to say gk. Now we come to the definition of a algebraic set. So you set X, which is a subset of this A subscript kn. This is called algebraic set if X is equal to the vanishing set of some ideal. So this V of I is an algebraic set. Now if the ideal is generated by a single polynomial, then we write it as V of f. Now all these three are examples of V of f. So this is V of x square plus y square minus 1. So this is an algebraic set. So this red circle is an algebraic set. Now this is V of y square minus x times x square minus 1. This is again an algebraic set. Now this is V of y square minus x square times x plus 1. This is again an algebraic set. So algebraic set here is drawn in red, here it is drawn in purple. So see, there are parts of it, this purple part and this purple part, similarly this. So these algebraic sets, they form the closed subsets of this AKN. Now let us give you some concrete examples. So say for K, so instead of K you can think of this as C of X. So you can think of this as C of X. Now the equation 0 equals to 0 gives the entire space as algebraic set. So 0 equals to 0 is the entire space. Now instead of 0 is equals to 0, you could have written 1 equals to 1 or 2 equals to 2. Now 1 equals to 0, this is obviously not true. So null set is also an algebraic set. So 1 equals to 0 is true only on an empty set. So this empty set is also algebraic set. Now equations of the form x minus a1 times x minus a2 equals to 0. Now the solution of this equation is 2 points, a1 and a2. So this gives you a finite set of points as algebraic sets. Obviously you could have written equation as x minus a1 times x minus a2 times x minus a3, but you have a polynomial, so there are only finitely many terms, so then you have 3 points. So for K you have entire space as a closed set, null set as a closed set, and these finitely many points as closed sets, or you can say algebraic sets. So notice that algebraic sets form the closed subsets. Now for K2, so for K2 you can think of it as C of x comma y. You again have 0 equals to 0, which gives you the entire space. Now we are talking about K2, so the entire space is something like this. Say C2, you have the entire space. 0 equals to 0, 1 equals to 1, and again 1 equals to 0 is only true on the empty set. So empty set and the entire space are also part of K2.
Points are also algebraic sets. So consider the line x minus a equals to 0 and another line y minus b equals to 0. So both these lines lie in C of x comma y, and their point of intersection is a comma b. So points are also algebraic sets. So later on we will see in Null-Stellensatz that the point a comma b corresponds to the maximal ideal generated by x minus a comma y minus b.
Now you also have curves here. So curves which are drawn like this. So these are all examples of algebraic sets. So you have curves like this. So this curve, this curve, this curve, all of them are also part of K2. So we can draw it like this. You have C2, you have curves in it. So these are all closed sets. Now an important remark is that if there is an ideal I1 which contains another ideal I2, so this ideal I1 is bigger than ideal I2, then the vanishing set of ideal I1 is contained in vanishing set of ideal I2. So this is kind of obvious, because if you increase the number of polynomials, then their vanishing set will decrease. So let us see this in an example. So you have the equation of a circle right here, and say you add to it another polynomial which is x equals to 1. So if you add x equals to 1 to it, you get another line like this, x equals to 1. Now initially this entire red set was where the polynomial x square plus y square minus 1 equals to 0 vanished, and x equals to 1 is this entire line. But when you want both of these polynomials to vanish, then both of these polynomials vanish only at a single point. These polynomials vanish only at this point. So this point is common to both these polynomials, x equals to 1 and this equation of a circle. So there is only one point left. So if you increase the number of polynomials, the vanishing set will decrease. So that is precisely what happens here. If you have a ideal which contains a smaller ideal, it has more polynomials here. So there are more polynomials here, and therefore the vanishing set has decreased. So there is an inclusion reversal process, and this is important to keep in mind. Now one final comment is that these closed sets are just these points or the entire space, and the complement of closed sets is the open sets. So the closed sets are finite set of points, and the open sets are complements of this. So notice that the open set is this entire space which lies outside these points. So these open sets are huge. Similarly here, this circle represents a closed set. The complement of the circle is the open set, and you can see this open set is very, very big. So it is important to keep in mind that in algebraic geometry, your open sets are huge, and there is rarely a Hausdorff condition which is satisfied. So you're not drawing an open neighborhood of a point, you're taking complement of a point, so that becomes almost the entire plane.